Okay, so we resume with talks, and now we discuss Z-prime models and model discrimination, as far as I'm aware. Maximilian from DESY. I'll give you the time. We should finish within 1 hour.
Yeah, it's quick and yeah. So welcome everybody, and thanks to the organizers for giving me the room to present this work here. So as we heard, this is about Z-prime models at a Muon Collider, and based on this paper here. This was a smaller project, let's say, together with two Ukrainian winter students, Katarina and Maria, who were at DESY in 2023, and also together with Christoph and Jürgen from DESY. Yeah, let's see. Can we get rid of this window, maybe? Okay. Let's see if this is enough. Okay, so the disclaimer for this talk, as you can see in this little saying here by Einstein, I think it summarizes it nicely, is that we want to have the simplest possible way of showing the power of a Muon collider, basically. So it's not a gigantic study of every process you could ever think of, but just basically the simplest way we could think of to exhibit this power. And as we will see already, this simple kind of study yields a pretty impressive reach for the collider setups we studied. The models we are studying, we are rather agnostic towards them. So we basically just look at a longer list of models in order to chart out a big map of all models possible in a given parameter space. And the idea, of course, would be to find at an experiment like a Muon collider some guidance into which direction of a UV complete model we are headed. So for the motivation, we all know that the standard model is impressively successful, but still can't explain everything. So the usual suspects when it comes to unexplained phenomena are dark matter, the baryon-antibaryon asymmetry, or also the question of unification. So whether we can find a unification of all forces at some point, not just the electroweak as shown here. And so again, the question is there a unification of the forces at some point? And is the standard model just a broken version of an enlarged symmetry group? Now, there's a multitude of well-motivated UV-complete models that contain various kinds of standard model gauge group extensions. But the thing is that most of them naturally come with an additional neutral gauge boson, which we call Z prime here. So some heavy neutral gauge boson that comes on top of the standard model ones. And what we do is we describe a larger set of models in terms of an effective Lagrangian, as you see here. So to the standard model neutral current part with the photon and the Z boson, we add another Z prime with different coupling, which again consists of vector and axial vector couplings, just as for the standard model Z boson. This here is the list of models we studied in our work. So you can see here the map of couplings that would then enter the neutral current Lagrangian in here. So the first example is the sequential standard model. And this is usually taken as a kind of standard candle for Z prime models because it has quite large couplings. So in the sense, over optimistically large. But this model doesn't represent the broken version of a GUT or whatever. Then there's E6 models, which are inspired usually by some low energy version of superstring models. Left-right symmetric models, which could be low scale effective theories of Patti-Salam or twinification. Then little Higgs or littlest Higgs models coming from compositeness or universal extra dimensions. And the U1X, which is a minimal U1 extensions of the standard model. I won't go into the details here, but the gist of it is you can see there's a large variety of motivations for UV complete extensions of the standard model, but all of those have a massive Z prime in common. And our goal is just to study representative cases of these models in the flavor universal case, where again, the goal is to basically chart out a map in the vector and axial vector couplings covering a large region of the parameter space there. Now, concerning the experimental setups, we all know that the most likely possibility for the near future is one or maybe even multiple of these machines. So some rather low energy precision tool for Higgs and electroweak precision measurements, for example, the Chinese electron-positron collider or some version of an electron-positron collider at CERN. And these machines would give us indirect hints for BSM models. But in any case, even if it is just in the further future, we would obviously like to have a high energy machine for direct access to BSM signals. And so even if the Muon Collider is not the next machine or whatever, we have to work with the idea of a high energy machine in the future. So this gives us the motivation to go ahead and study the Muon Collider. Now we've probably all seen this picture by now. It's some schematic representation of a 10 TeV Muon Collider, where the usual pros that one mentions here is that you have point-like partons at high energies as compared to a high-energy proton-proton collider, where you would again run into the trouble that you have at LHC for the uncleanliness of the processes you study. With the big advantage of the Muon Collider being that you have a factor of 10 to the 10 less in energy loss per turn, but of course also some contrapoints. Obviously the short lifetime of the muon, but it's still manageable at the energies that we are talking about. So you would have a 150 milliseconds lifetime effectively. Then beam-induced background, high neutrino flux, and other problems, you name it. But the important message I like that has been mentioned in this paper is that it's challenging but not impossible. So let's hope that this is true as they state right here. For us, it's important to mention that we study these variations here of the Muon Collider, so 3 and 10 TeV with this relation for the integrated luminosity. So basically 10 inverse autobahn for 10 TeV. Yes. Now, what do we actually study? It's really simple, just S-channel lepton production at a Muon Collider. So this is basically the full set of diagrams. Just muon collision into E plus, E minus, or tau plus, tau minus via gamma Z and Z prime. This has the advantage that the same couplings enter here and here. If you would also look at quark production, then you could have different couplings of your Z prime to the quarks, which we would also have to fix somehow. So this is really the simplest version possible. Then what you see here is the total cross-section of a center of mass energy for a list of Z prime models. And depicted here the region that we are interested in. So we think about rather heavy Z primes that go beyond the reach of the Muon Collider and want to extract information from here. And one reason is that the Born approximation already gives reliable results in this region. If you want to go, if you want to have a peak study, NLO contributions shouldn't be neglected. So anyway, this makes the analysis very simple. And so simple that you can do it fully analytically, but we also check this in Wizard. So the Monte Carlo generator, currently mostly, I don't know if you say mostly developed by Jürgen, but one of the main contributors there. So if you don't know it, it's a general purpose Monte Carlo generator for all kinds of processes, both at lepton and also proton machines. And important for us is that it also has a full UFO model support. So any BSM model that you can put in a fine rules file can directly be used in Wizard and used for studies like this. Now, because then you would have T-channel contributions as well. And on the next slide, you will see that we are interested in asymmetries above all. And the asymmetries would be spoiled in if you also have T-channel contributions. Of course, you can also add mu plus, mu minus there. But as I want to show you here, what we are interested in are, for example, the forward-backward asymmetry, which is the simplest in these cases. No? So, as I said, one of the observables we're interested in is the forward-backward asymmetry, which has been known for a long time, also in the standard model. So this is from the Böhm-Danner-Joos QFT book, E plus E minus to mu plus mu minus, and you see that the distribution you get here in the final state angles is not symmetric. And how this comes about is interference contributions of this kind here. So if you look at a squared matrix element, you can see the influence of interference between photon and then Z, or either Z or Z prime. If you plot, so you can define, instead of just the angular distribution, just one number, the forward-backward asymmetry, which is the difference between forward and backward events, normalized by the total cross-section. And then this is what it would look like in terms of the center of mass energy for a Z prime model with a Z prime at 10 TeV. So this here is at the standard model Z, this interesting dip peak structure. And then you would just have another one at the Z prime mass that depends again on, so the exact shape, of course, depends on the couplings of your respective model. But what might be nice to show here is exactly how these peaks come about. Again, I told you this is the reason for this are these interference amplitudes here. And you can see this in the plot by this orange dashed line here, giving the main contribution for this structure. And then the violet one here coming from the Z prime, giving this other one, while the self-energy-like contributions or other interferences don't play much of a role for them here. Okay, so again, the list of observables we put in the study is just the total cross-section, as I've shown you before. Then forward-backward asymmetry, what I've just shown you. And here you now see the list of all the models and how they would look like around the Z prime pole. But of course, all giving you the same structure at the Z mass. No? Then similarly, but different, is the left-right asymmetry. So for the polarization of the initial states, you can define this just like the forward-backward, but for different the difference in the polarization states. And you could see an asymmetry like this here, so potentially even more pronounced than the forward-backward asymmetry. And similarly, the polarization asymmetry, which is the polarization of the final state stuff, which we would measure in the experiment. So this here you would set up by polarized beams in your collider. This here you would set up by measuring the polarization of the final states. And for massless fermions, these are equivalent, but experimentally they're very different, of course. The access to them is very different. So again, this is an example for a 10 TeV Z prime, so sitting here for this list of models that I've shown you before. Hmm? Yes. Exactly. So that's why we used it. No? Again, as I told you, we are working in the off-peak region, so around here, where you can already see significant deviations. No? If you were past the peak, it would be much more severe, obviously, or around the peak. But already this is already good enough. Yeah, that's what we see in the results later too. No? Yeah, again, the statistical analysis, very simple, just the usual chi-square, where we measure the difference between, in this case, the standard model expectation versus the observables. So for example, the forward-backward asymmetry for a given axial vector and Z prime mass. I mean, axial and axial vector coupling and the Z prime mass. We can talk about this term here later if you want to, but it's just a technical detail. And then we look at the regions which determine the 95% confidence level for deciding whether we can exclude this model or not. Same for the statistics, or I mean for the error analysis, very simple, just geometric mean of statistical and systematic errors. And at the luminosities that we work with, the statistical errors will usually be around the percent level. And we set this also as a goal for the systematic errors. So we don't do a full-blown systematical error analysis for some given Muon Collider setup, but we would instead claim that this here could be a goal for the systematic error that the experiment should aim for. Or just a different way in thinking about it. The only exception is the measurement of tau polarization, where we assume a larger error, and this is well inspired or taken from a lab experience where it turned out that it's hard to get below this kind of precision. No? But we will see the influence of choosing this error bigger or smaller later. No? Exactly, that's what I just said. So the idea is to perform a study to see which error you should aim for to get reasonable results or useful results. So here, these are the results for the mass reach. Again, the chi-square I've already shown you, and we fix the couplings for a given model and then vary just the z prime mass to get the limits you see here on the right. How they are different for the models, obviously, or I mean, quite different. For example, for the alternative left-right symmetric model, you get this very high mass bound around 70 TeV for a 10 TeV machine. And this is because the axial and vector couplings in this model are quite large, so you can exclude a large range, or you can find a Z prime up to quite high masses, even just for a 10 TeV machine. While the current limits, this is also worth mentioning, maybe at LHC are in the 5 TeV region. So I think this is a quite impressive reach, as I was trying to, or as I was advertising before, for a 10 TeV machine, given this extremely simple setup. So adding any more information will only drive this up even more significantly. No? So this is what I mentioned here, that the effective polarization barely influences the mass reach here. The polarization is important for the measurement of the couplings though. No? So this is based, as I said, barely influences means, you get deviations by maybe a few percent or whatever. They are so because you see that I mean, just effectively, you can see it in the total cross-section plot, where again, asymmetric left-right or U1X, for example, give you the largest deviation from the standard model case here, no? While other models are much closer to this line here in the middle. The couplings, yes. Again, I mean, I don't have numerical values here, but these couplings are quite different. Now some are, very small, closer to zero. Others are quite large. Mm-hmm. Favor universal in this, yes, I mean, that's what we said as a
I mean, they are flavor universal in the sense that they couple to the same way charged leptons, neutrinos, quarks, but I mean, of course, the coupling of quarks and leptons is different. And up-type quarks and down-type quarks is different. Yeah, that's right, but they're all in about we can use leptons. I mean, if you would, and actually, it's not true that all of these models are fully flavor universal. For example, the models which like extra dimensions or little hicks, they have different couplings. We didn't include this, so the mass reach would become much bigger.
Yes. Well, I mean,
There is this.
yeah, no, they're very consistent, just at a higher mass value, obviously, no. I don't know where we found this. I mean, it's I don't think it was just a single process, but overall bounds. So it's already a combination of results, not just the analysis that we did at LHC. No? But anyway, what I'm trying to say is there was much more work done at LHC already to arrive at this 5 TeV bound, whereas again, this very simplistic analysis yields these rather high bounds here, no? Which would go much further if you were doing the same analysis as at LHC. I mean. One again? I mean, we have more plots on the next slide for the axial and vector couplings. So I mean, in this sense, you could think about a 3-parameter variation: mass, axial, and vector coupling. But of course, for a given model, there's relations between axial and vector couplings. But if you think of the effective Lagrangian, then you have, I mean, the effective C prime Lagrangian, then you have axial and vector coupling plus the mass. No? So it's these 3 parameters. Mm-hmm. Yeah, no, it's true. Okay, but again, we do a similar analysis, but for a fixed C prime mass now, and vary the axial and vector couplings, and then combine all different observables that I've showed you. And now what you see here are plots in the axial and vector coupling plane, and the bounds you would get for each of these observables. So the total cross section would give you these elliptic regions, while these asymmetries give you these hyperbolic ones. And you see the nice thing about them is that they are very complementary in the plane of these 2 parameters. So now we combine those and end up at these plots here. So now what I show is the resolution power for axial and vector couplings for this type of machine. So 10 inverse autobahn, 10 TeV, and no polarization for now. But you measure the polarization of the final state taus with some precision. And what you can see here is how well you can discriminate between the models for different values of the masses, so 40, 30, and 15 TeV. And what I want to show here is that already for a mass of 30 TeV, you have quite some resolution between different models. You still have some overlap between some of them, like the alternative left-right and the U1X. But anyway, you're already getting somewhere. While of course for lower masses, when you get closer to the peak region, the distinction power would be much more impressive, obviously. So even without polarization, you already have some resolution in this plane. But now we also study the influence of polarized beams and polarization measurement. So what happens from here to here is that we include an effective polarization of 30%. And then you can see these regions here disentangling. So what this means is via effective polarization, you can measure the sign of the axial vector coupling. And interesting to see maybe is that even without an effective polarization, so no polarized beams, but just a more accurate polarization measurement for the final state taus, you would get basically the same or even better discrimination between the models. And as I said, you can now see this as setting a goal for the experimental precision or for your setup in terms of polarized beams or not, if you want to be able to measure the couplings or the signs of the couplings at a given accuracy. Yes. For tau, yeah, just tau. That's it. No, I don't know if we included electrons, but I think it's really just tau in this case. No, as it was done for lab, so it's basically a scaled-up lab analysis. No, that's why we would be. No, not yet. This is what I mentioned here, that obviously there's loads of room for improvement. So you can now go ahead and do the same analysis by adding quark final states. But then you run into the complication that quark and lepton couplings are different depending on the model. So it would be a bit harder to make this kind of 2D plot. No? Yeah. So, yeah, maybe. Whatever. Yeah. It depends on the precision. So here we assume a 5% systematic error on the tau polarization. And if you have this kind of large error, then the polarized beams would help significantly. No? So the difference between this and this is that you have polarized beams at 30% effective polarization. And this helps you measure the couplings, obviously. No? But it is, so polarization of beams is redundant if you are very accurate in the polarization measurements of the final states. But I'm not sure if this would be technically possible even. So this would need to be studied. No? Yeah, so it's a trade-off between the two. What again? I mean, it's not very hard. It's just a bit harder to show plots like this because you would have, you would always have to fix two couplings and then do a variation of the other two. But of course, speaking in terms of coding or whatever, it's basically trivial. No? Yes. So I mean, the points represent the exact values of the model couplings, no? And say you do, you have a measurement right here. You get an experimental value of, this here and zero axial coupling. Then you sit inside this region and you cannot exclude the E6 model. That's the spirit behind this. So basically, you're consistent with the E6 model. Yeah. Well, that everything in here is consistent with the standard model. So you could not see the difference between this little 6 model and the standard model, or you could not claim a discovery. No. While again, if you land here, you could say we don't have the little 6 model. something like this. So again, it tells you if your measurements are accurate enough to say whether you're consistent with a given model at 95% CL or not. No.
Once you are not consistent with it, you want to differentiate yellow from purple.
Yes. Yes. Yeah.
May not know if it's yellow or purple.
Yes. Yeah. Again, we already said that this analysis is really quite simple. So of course, there's lots of room for follow-ups and improvements. You could think about including hadronic observables. And again, previous studies for lab have shown that this would drive up the mass reach by around 50%, for example, depending on the model. You could combine with LHC results or even high lumen LHC prospects. Also put the mu plus mu minus final states in, but then again, the asymmetries wouldn't be as distinctive as they are for a plus and minus, but okay, why not? No. Or also extend it closer to the peak region, but then again, this would require a more sophisticated next to leading order analysis to be yeah, realistic. No? So again, the conclusion for this talk, I've tried to show you a list of well-motivated Z-prime models and that the Muon Collider would be a very powerful tool for finding and resolving them. So as I've shown you, a 10 TeV Muon Collider could already put or find Z-prime bosons up to 70 TeV mass range. And for masses of around 30 TeV, even for a relatively simple experimental setup, you would already get a very strong distinction power between the models, as you see here again on the right. And I've shown you how polarized beams or accurate measurements of the polarization can significantly help in the distinction between models. And with this, I thank you for the attention.
We already had a bit of discussion. I see the question there.
Yeah.
Can you just wait a moment for the recording?
I mean, these lawnmowers are really loud, but okay. Otherwise, I can hear you.
So can you go back to slide 12?
Hmm?
I think it was it. Because you said you're excluding the peak region. Like, it was just a little confused because it looked like you had exclusions for the peak regions.
Exclusions for the peak regions.
Because of like 10 TeV, you're showing you're excluding Z primes with mass below 10 TeV.
Well, I mean, I'm not sure how to say this. Now, the analysis kind of automatically only goes up to a certain point right here when, or let's say, you, in some sense, you would be coming from the right and going as far as possible. You know, when the deviations become so small that you can't see them anymore, and then this point here coming from the right would be your mass bound in a sense. So I mean, you could also plot this in terms of the Z prime mass, and then it would look similar, but coming from the other direction. And then you basically go beyond the peak into this off-peak region. Okay. Yeah.
Maybe polar colors, darker colors are for a species. And then you are still out of the peak.
Yes.
Like the US model, the full thing is below 10 TeV, but it's only for a 3 TeV, by the way. You can be below the rest.
Okay. Okay, thank you.
So for the U1X model, if you could go back to the charges, I think you fixed the charge to some particular values there.
Yeah,
But
so
if I remember correctly, the U1X is a class of models where you can have different types of charges, like depending on the two Higgs charges, basically X8 and X5. So if you use other values, then did you also check how the bounds would change there?
no, see, we only use one representative case for each model. No? So some choice of parameters. For example, for this alpha here in the left-right symmetric model, you would also have some range
Right.
that would be allowed within the model, and we just choose one value that is, you know, not crazy, big or small, just some representative value.
Is this the one that gives the maximum reach, or
No, it's let's say just common choices that people use in these types of analysis. So not the boundary values that are usually possible, but something in the middle range for the couplings. No? So kind of like a you know, central value, let's say, for the couplings.
Okay.
Yeah, I think the spirit is to show that you can have some discrimination power, but if you really ask what's the model like, the question is infinitely dimensional to an extent.
No, sure. No.
In fact, to this end, I think Jürgen mentioned that some couplings are also differentiating left and right quarks, left and right fermions. And in at least last week, we discussed as well radiation. So all of these, I imagine, I don't know if you agree, that it can be addressed with radiation. So you can add photons, you can add Ws to those signals, and especially with Ws, you can access the charged currents. And they are also chirally sensitive to left and right fields. I don't know if you have looked at if there is any hard question out of those models that can be distinguished by adding radiation of this type, especially for which is a substitute kind of for polarization, as we discussed last week.
Yeah, no, we haven't tried to include this yet or whatever, but of course could be put on the list of future studies. No.
So any more comments or questions? So I wanted to add the ZH. ZH is also, at some point you must develop also a final state ZH, I suppose. Yeah, the Z, when it's not fully vectorial, I think the Higgs has to become charged under one of those.
Well,
Quantum
I mean,
no.
Like, for example, generic dipole for the moment. But I mean, the ones that are, I mean, first of all, clearly, like BB bar and TT bar as final states, right? Because then you get different
I mean, one thing that you were wondering at some point was whether there is a way of, from the analysis point of view, right, to organize the study in terms of arbitrary models. So not to pick models. Okay, but so for example, you could think of generating sample. So take this model here, right, and then say, you know, I generate 3 samples or 4 samples. I didn't make the calculation, but for each v square, va, v and a square terms, you know, and then make a basis from the Monte Carlo point of view that then you can do any model of this kind, right? So that you don't have to. So whenever anybody comes, and then you say, okay, which one is your model, and you just reweight what you have done, and you get anything without rerunning every time your given model and so on. You see what I mean? So
I mean, yeah, I'm not sure if this is to some extent included in this region that you talked about. You know, this blue region here. This would be the, you know, generic distinction between anything from standard model, basically. I don't know
No,
if
no,
this
I-
is
no.
what you're headed towards or something different.
I mean, there are so many different models. We discussed this already in other contexts. And so what people have their own ideas of what is a different model. And I'm sure that you show this list to some big conference and only someone say,
Yeah,
well,
yeah.
my model is not
Yeah,
there,
yeah.
right? And then you just say, well, just give me your model, I run it, and then tell you. But the other way would be that, you know, that to organize the information in such a way that you have coverage all models,
Yeah.
right? And you don't have to pick up any.
I mean, for example, if you could define a model that would have a coupling here,
Yeah.
you know, you could fill up this space, obviously. But as you see, we try to pick models that, you know, have some distinct spot in this plane here. No? So of course,
Yeah, I know. Yeah.
there's more models similar to little Higgs, which would land in the exact same spot here. So it doesn't make much sense to put, you know, 3, 4 dots on top of each other. It's just charting out this map, no, as you know, in a as large parameter space as possible. Hence this choice of
Yeah, I'm wondering whether there is a way of communicating the information in plots, so
Yeah.
that anybody with any model can just combine the information from each plot, and then you get what the limits. Right,
Yeah,
that's
not
my question.
sure. I mean, to get this plot, you need to assume something on the couplings. Now you test your measurements against a hypothesis, and the hypothesis would be here the E6 model, for example. You know, while you can't put nothing as a hypothesis. You know, I mean, this would be in some sense the standard model. The hypothesis would be that there are no axial vector couplings.
So there are two different. I mean, there are two different questions, right? I mean, exclusion and discovery. If you inject the new model, I mean, you have various possibilities. But what I'm saying that again, I believe there might be a way to do an orthonormal basis in such a way that once you have the information on 3 cases, you can get any.
No, no.
Okay. So
I mean, what possibly do is that you could make the assumption, okay, we have at 95% confidence level, we have excluded the standard model, and we have basically established that there is a C prime resonance, some new neutral current, whatever. And then you start doing different assumptions on observables that you include and measurements and systematics, and then that would give you ellipses of the C prime vector and axial vector couplings, so certain patterns in this space. And then everybody can start fit their favorite model to that experimental precision in the measurement. We did the opposite way. We basically said, okay, these are the regions compatible, right? And if the measurement becomes that and that precise, you can discriminate between this and that model. But I think it's basically like contrary views somehow.
I don't know if I interpret Fabio's question, but I think he's asking for what is this MEF subset that you should apply for these kind of things, or close to that. So there is only remove the on-shell case, take it only off-shell. Which operators are you generating? After you take into account that they have to be some assumption on flavor, and for sure you want to respect electroweak SU2. At that point, you may have a family of operators, and these are, I don't know, a number, 9 operators that makes you 9-dimensional likelihood. This is what you would do under the flavor assumption to test any Z prime model. Then maybe you want to make it flavored, and there become 27 operators, or 81, or another number. So I guess that's the exercise that you were mentioning, that it could be very useful to know the full set of operators that arises from a generic Z prime, which after all can be coupled to quarks and leptons, left and right. Otherwise, you bring SU2, for instance.
I agree, you can do that. The question is, and I have absolutely no answer to this, but maybe somebody is whether this play with the operators is actually a faster or an easier way to the UV complete model, or the fit with the, I don't know, making.
You need some back and forth. It took me a week to do a model to be sure I was not missing anything, and probably I already still miss something.
No, but
that's
maybe a
it.
question.
I think we were probably fencing about, and
Then
that's just a naive, probably way of putting it in terms of math coefficients.
but a question from my side, and how well developed are matchings between these types of explicit UV complete models and SMEFT? So, some list of C primes that have explicitly been matched to SMEFT, for example.
I'm not a professional,
Yeah.
I admit, but I think this Granada dictionary is one tool one can use, and maybe there is even some automated tool at this point that can help with that. But I'm not very familiar with those. That's why I spent 1 week making mistakes.
Yeah.
And trying to get which were actually usable.
Write it up and send it to us. Write it up and send it to us. The exercise that you did with the operators, write it up and send it to us. It's useful.
Well, let's do it in private. No, but yeah, this already gives a clear picture of potentially the power that can exist. And well, maybe for a different time we can discuss FCC, HH, and stuff like that. So I have the less powerful mic now, but still, if you have any further question, that's we have some time, or otherwise we move to coffee. Okay. More powerful. So we thank Maximilian once more. He's going to be around.